All right, exciting time right now. This is it. We have reached the fundamental theorem of calculus, and there's two parts to it, part one and part two. And usually I abbreviate the fundamental theorem of calculus as FTC, and then if I want to talk about part one, I'll write the number one. Part two, I'll write the number two. So this is really the theorem that sort of connects, if you will, calculus 1 and 2, the way we split it up, the so-called differential calculus and integral calculus. And it's really going to connect the two ideas we've been developing so far, the idea of the definite integral, which kind of one of the things it represents is the area under the curve, if the function indeed is positive over that interval. But it's the definite integral, and then the indefinite integral, which was the antiderivatives. How do these things connect? And this is going to be it. First of all, before we do it, I'm going to prove the theorem. I want you to recall from Calculus 1 the mean value theorem, which is an important theorem in Calculus 1 we learned. It's really important because it's used in proofs of other theorems, for instance, the fundamental theorem of calculus. So here's the mean value theorem. If you remember, if f is a continuous function on a closed interval, right? So continuous meaning there's no holes, gaps, jumps, breaks in the graph, vertical asymptotes, and so on. That means that the function exists at every point and the limit exists at those points, and they are both, those values are equal. Both of those values are equal. It's also differentiable on the open interval. Differentiable adds a little bit more, right? If you're differentiable, you're certainly continuous, but differentiability means you're basically smooth, if you will, and continuous. There's no sharp turning points, right, where the derivative would be undefined, no vertical tangent lines, etc. Okay, with those conditions, then on this interval there's at least one, if not more, values, C we're calling them, in this interval. So input value C, such that the derivative of this function, right, since f is differentiable, right, we have a derivative, its derivative is equal to this expression. So you should recognize this expression as being the essentially average rate of change of this function over the interval from A to B. Let me just illustrate it graphically. I think that is really helpful. I'm not going to prove the mean value theorem here, but I'm going to look at a function here, f, and going from A to B. And of course, we look at the 2 points on the graph at A. That is the point A comma f of A. And up here we come up to the point B comma f of B. Right. So now, if I take and draw a line connecting these 2 points, right, then the slope of this line is equal to the average rate of change of the function f over the interval from A to B. And we can see that because, remember, slope is rise over run, or vertical change over horizontal change. So what's the vertical change? It's the difference in the y-coordinates as I go from point A to point B. So that's the f of B minus f of A. So the slope of this, f of B minus f of A, over the horizontal change, right, the x change, right, which is the difference in the x-coordinates, B minus A. Right, that's the slope of this purple line, and that indeed is this expression here. That's the average rate of change of the function over the interval from A to B. Okay, and what we're saying is that the derivative of this function at some point C, so C is somewhere in between A and B, right? It's in between A and B, somewhere in here. The derivative, we're guaranteed at least once, is going to be equal to this value. So what's the derivative? The derivative is the instantaneous rate of change of the function, right, at a point. So if I pick a particular point, like right here, right, I'm going to draw use the bottom of the ruler to be the tangent line. So just touch the graph right at that point. The slope of that line, right, is the derivative at that point, right? That's what the derivative means, right? And as we're moving, notice that the instantaneous rate of change, the derivative is changing, right, as we move from left to right. It's positive, it becomes 0, it's negative, 0, and then positive again. So it's changing. But we're saying that at least one point on the interval from a to b, the slope of the tangent line, the derivative, right, f prime of c, is equal to this average rate of change. We're saying another way, the instantaneous rate of change at some point from a to b is equal to the average rate of change. Do you see where that occurs? Give you a second to think about that. Let me help you. It's going to have the same slope as this line, so in other words, the tangent line will be parallel to this line. So I'm going to put my bottom of my ruler right on that line, and I'm going to move it in a way that keeps the bottom edge of the ruler is parallel lines that are parallel to that purple line. So they have the same slope, right? The bottom edge of my pink ruler. And I'm going to move until what? Until I just touch the graph of the function f, right about there. And now I'm going to draw that line. I'm going to draw this in red. Right? So right about there, that red dashed line, that's the tangent line, that's the slope of that line, that's f prime of c. Slope of that line is f prime of c. Well, I'm going to call that c. So in other words, that I'm saying the value of c then is where? Here. That's the value of c. So we're guaranteed to have at least one value. Do you see that there's actually two values? That where the derivative of the function is equal to this average rate of change? Yeah, there's another place. If I look again at parallel lines, this time moving down, I will just touch the graph right about there, approximately. Right about there is another value. We could call it c, maybe c sub 1, c sub 2. I don't know. So two c values, right? Two different ones. So we could have more than one. There could be many. Okay, especially if you think about it, the function sort of moving up and down a lot, we could have that situation occur. Okay, but that's the mean value theorem. It's just sort of an existence theorem. It does have some application in the sense, like I said, it's kind of neat that you can say for these type functions, for continuous functions that are differentiable, that we're guaranteed that the instantaneous rate of change, the derivative, is equal to the average rate of change. Okay, so if you're driving down the highway and your average speed is 60 miles per hour for 2 hours, you're guaranteed to have been traveling at 60 miles per hour at least once. Okay, I mean, your speed obviously might fluctuate, slow down, speed up. On the average at 60 miles, but we know then that you're traveling at one point in time at least that speed. Okay, but what I'm going to use this now is to prove the fundamental theorem of calculus. So we're going to put this in the background and we're going to bring it back up in just a minute. So here it is. This is the real theorem that we're interested in here in Calculus 2, the fundamental theorem of calculus. And I'm going to prove it, and then the rest of the lecture videos will be just applying it. And that's mainly what you're going to be doing, but I want to at least show how this is working. So here it is. Again, the function f is continuous on a closed interval, so sort of like the mean value theorem. And in that case, the integral from a to b of the function f of x dx, the definite integral of this function from a to b, is going to be equal to, this is little f, capital F of b minus capital F of a. So what's this capital F thing? Well, where capital F, the derivative of capital F, is little f. In other words, capital F is the antiderivative of little f. So you see, this is the antiderivative is the indefinite integral, right? The indefinite integral of little f is big F, right? And so here's the connection. This is the definite integral, and we can evaluate the definite integral by using the indefinite integral, if you think about it. Evaluated where? At b, which is the upper limit, and then at a, which is the lower limit, and subtracting. It has to be in that order, right? Subtraction, you can't commute subtraction. It'll be the opposite sign, okay? Notation that we use here is this. For f of b minus f of a is the antiderivative, and a vertical line, and b and a. This vertical line means evaluated at. So we're going to evaluate it at the upper limit of b, evaluate the lower limit at a, and take the difference. So this is the notation we'll use. So this is really incredible, because what this is saying is I can find the value of the definite integral by simply, over the interval from a to b, right, by simply evaluating the antiderivative of this function at just the endpoints. Right, at just the endpoints. So you think about what this integral represents. If f is indeed positive over the interval from a to b, this integral represents the entire area. Let's just say the function f is continuous and positive over the interval from a to b. Then what do we know? We know that this definite integral would indeed represent this area that I'm shading in, right? But the cool thing is we can find this entire area. This function's doing crazy stuff changing. We just take the antiderivative, evaluate it at b, evaluate it at a, and subtract. Think about how much work we've been putting into the limit definition of the definite integral, how long that process has been. Getting the expression for the, say, right-hand approximation, and then taking the limit as n goes to infinity, right? That's a lot of work, and we can't do a lot of definite integrals that way. The functions have to be very specific types, right? So this is a groundbreaking thing. Okay, let's prove it, and then we'll use it. The proof goes like this. We're going to partition the interval a to b into n equally spaced, I'm going to use equally spaced subintervals of width delta x, which will be what? B minus a over n. I mean, this is nothing more than what we have talked about already when we talk about the definite integral before, right? This is the process we went to estimate. We're going to let the endpoints of these subintervals be, of course, a, which is x sub 0, x sub 1, x sub 2, all the way down to x sub n, which is going to be b. Remember, that's our notation. We start with x sub 0, which is a, then delta x to get x sub 1, delta x more to get x sub 2, and so on all the way to x sub n, which is b. Right? That's what we've used before. Okay, so this is the partition, we call it, remember, breaking it up into subintervals. Now, here's what we're going to do. Capital F, right, was this antiderivative. So I want to look at f of b minus f of a. I want to start there. I mean, that's ultimately going to be what we want to connect here in a minute. I'm going to write this out a little bit differently. Okay, f of b minus f of a. I'm going to write it as f of x1 minus f of a. By the way, remember a is x sub 0. So there's going to be a pattern here. Okay, so this is the first subinterval. I'm going to, this is from the, the end point of the entire interval from b to a. This is just the difference of the function capital F at the endpoints of the first subinterval, right, which goes from x sub 0 to x sub 1. And then I'm going to add the second subinterval, f of x sub 2 minus f of x sub 1. The second subinterval's endpoints, if you will. I'm going to subtract the in that order, basically from the right endpoint minus the left endpoint in each case is what we're doing. I'll do one more. F of x sub 3 minus f of x sub 2. Okay, and that pattern I'm going to continue all the way down to the last. Let me do the last two. This one will be f of x sub n minus 1 minus f of x sub n minus 2. And then I'll have f of x sub n, remember that's b, minus f of x sub n minus 1. Okay, so well, you're wondering, how am I saying this is equal? What's all this junk? What's happening here? Well, take a look at this. If you think about simplifying what I've written over here, notice this f of x sub 1 here, plus what? A negative f of x sub 1? What's going to happen to those f of x sub 1s if we combine like terms? They're going to go to 0. F of x sub 2 minus f of x sub 2, that's going to go to 0. this f of x sub 3, the next one over here will be, in this dot dot dot, will be minus f of x sub 3. It will cancel. Back here, there'll be a f of x sub n minus 2 minus f of x sub n minus 2 is 0. F of x sub n minus 1 minus f of x sub n minus 1. Okay? All those cancel, and all we're left with is this one, f of x sub n, or f of b, right? It doesn't have, right? There's not another one after that. And this minus f of a, there's no positive f of a anywhere. No positive f of x sub 0. And so what are we left with? F of b minus f of a. Okay? But they are equal. You might say, why would I go through this process? Well, proofs are a little tricky sometimes, but you can kind of see where I can now write this right as a sum. I equals 1 to n of what? F of x of what? It's 1, 2, 3, 4, so it's x of I here, minus f of what? It's 0, 1, and so on, so it's 1 less f of x of I minus 1. Basically, this is just in general the difference of the function capital F at the right endpoint minus the left endpoint of the ith subinterval, if you will, the ith subinterval. Okay, so what we've done is we've breaking it up again. We're just breaking it up into these n subintervals, and what I'm going to do is on an arbitrary one of these subintervals here, the width is delta x, I'm going to come up here and look at the function f on that interval, and I'm going to apply the mean value theorem to it. In other words, this function is going to be continuous, right? And it's going to be the capital F is also going to be continuous because it's going to be differentiable, right? Since it's the antiderivative of f, it's differentiable. So I am looking at actually not little f function again. I'm looking at big F function again. So change this to big F. I mean, that's what I'm going to be looking at. I'm partitioning the axis for big F. And on that small interval, I'm going to apply this mean value theorem, right? This mean value theorem right here, and saying that on that little short interval, the average rate of change is going to be equal to the instantaneous rate of change at some point on that interval. So that's what I'm going to do now. By the mean value theorem, there's my abbreviation for that, there is a, and I'm going to call C sub I because for each subinterval there's a C. The C that exists in the interval is going to be different possibly for each subinterval. In the ith subinterval, which would go from x sub I to x sub I minus 1 to x sub I, right? Right and left endpoints there. And what? Such that capital F prime of Ci, the derivative of that, is equal to f of x sub I minus f of x sub I minus 1 over the change in x, right? Which is basically x sub I minus x sub I minus 1. But remember, the width of all these subintervals was what? Equal delta x. So I'm just going to write it as delta x. And so that, if I just rewrite this, if I multiply both sides of this equation by delta x, then I have f of x sub I minus f of x sub I minus 1 is equal to f prime Ci times delta x. So multiply delta x both sides, right? Okay. All right. We're almost there. Let me even change color here to emphasize. So hence, what do we have now? Go back up here. Capital F of B minus F of A is equal to this summation I equal 1 to n capital F of xi minus f of xi minus 1, right? But this inside here is right here. I'm going to replace that with f prime of Ci delta x. So this is the summation I equal 1 to n now of f prime Ci times delta x. Now, what is f prime of Ci? Remember, capital F was the antiderivative. Capital F prime is little f. So this is nothing more than summation I equal 1 to n f of ci delta x. And now, look at this. What do we have? What is this? What is the summation? This is a Riemann sum. It's a Riemann sum, right? Think about the f of ci times delta x. These are like the rectangles, right? The height of the rectangle found by the point ci on the subinterval. F of that gives me the height times the width, delta x. That's the area of the rectangle. Add them all up, right? It's that same idea that we developed, right? It's a Riemann sum. And so what do we have? As n goes to infinity for both sides of this equation, right? What do we have? We have f of b minus f of a over here, right? That doesn't change because these are just fixed values. They don't change with n, right? A and b are fixed. It's always been fixed. But here, what happens to this? As n goes to infinity, what's happening there? We take that Riemann sum, we push the limit as n goes to infinity, our delta x gets smaller and smaller. We have in the limit what? Provided it exists, the definite integral. That's the definition of the definite integral of the function here, which is little f, right? And that's the proof. That's the proof. Why? Because, right, as we said, the integral of little f of x, right, from a to b is equal to capital, the antiderivative, f evaluated at b and at a and taking the difference. Okay, well, there's the proof. I don't know how satisfying that was for you. It was pretty satisfying for me. It's a powerful theorem, okay? You won't have to prove this unless you're a math major, maybe later on, but you will have to apply. And so in the next set of videos, we will spend time applying this, and that'll be a lot easier than what we've done here.